I'll tell you a little bit about Laura. She was an undergraduate at Ohio State, did her PhD at Cornell. She went from graduate school to Bell Laboratories, where she worked for a number of years. And like many of us who worked at Bell Laboratories, we were then fortunate to be able to move on to positions in universities. In her case, she went to the University of Illinois Urbana-Champaign, where she had an extraordinarily distinguished career as a solid-state experimentalist. She used various experimental techniques to study unconventional superconductors, which is what our meeting is about this week, and you're going to learn a lot more about them in the next 45 minutes. And her specialty, as you'll hear, was tunneling and point contact spectroscopy. A couple of years ago, she moved to Florida State, where she's the chief scientist of the National High-Field Magnet Lab, and also the associate director of the Center for Emerging Superconductivity. Of course, someone with her accomplishments has received lots of honors. She's a fellow of the American Physical Society. She won the Department of Energy's E.O. Lawrence Award. She's a fellow of the American Association for the Advancement of Science. She's a fellow of the American Academy of Arts and Sciences. She's a fellow of the National Academy of Sciences, and so on. I'll say a little bit about her. Besides her scientific career, she's basically essentially duplicated herself and has had a parallel career in public policy. And she's played an active leadership role in numerous science organizations. In this past year, she was president of the American Physical Society, which oversees all of us physicists. Her presidential theme was science diplomacy on national and international scales and its application to human rights. And I'm not going to ask you about the current political climate. She currently co-chairs the Decadal Survey for Materials Research for the National Academy of Sciences, which comes once every 10 years. She's vice president of the Executive Council of the International Union of Pure and Applied Physics, and she chairs the organization's commission on the structure and dynamics of condensed matter and its U.S. international liaison, and it goes on from there. So she's made extraordinary contributions, but besides being a great scientist, she's also been a great leader in our community, and we're really grateful that she was willing to come here to Aspen this week and to give the talk. She's giving both a technical talk and then also agreed to give this public lecture tonight. Laura.
Thank you very much. Thank you very much, Bob. I'm just very, very honored that Bob Bergeneau was introducing me. I've known him for many years, have great respect. And I'm also very nervous because the director of my Center for Emerging Superconductivity, Peter Johnson, is here, and the director of the Magnet Lab, Greg Bobinger, is here, so I better do well. So basically, I just want to say why I chose this title. And I chose this title for these reasons right here. One is that I want to get across that quantum materials, the thing that make your computers work, your cell phone work, and I'll give you some other applications, are a fundamentally unsolved problem. Then there's a whole array of them. And so, as many of you know, if you've gone to these lectures, dark energy and dark matter are also unsolved problems. And I have a kind of a fun analogy that I found also that people that are working on dark energy have also used superconductivity as an analogy. And then I also want to tell you, and I just wanted to mention David Pines, because I think probably many of you know him. He has a house here. He can't be here now because he's in Urbana, Illinois. But he did some of the original theoretical work about 70 years ago that got this field going. Another thing is I'm not going to talk much about my research at all. This is more of a view of about from 35,000. I've been doing this work on these materials for decades. They're incredibly consuming and seductive, and I just like thinking about it. And this conference here, if you just look at the speakers, it's just been tremendous and exciting, and I'm just glad I'm here as part of it. So these are the topics. I'm not going to read through all these right now, but I want to go through a little bit of the MagLab. I want to tell you what a superconductor is. I want to tell you what a high-temperature superconductor is. And it's not very high temperature. And also, then that will lead to what is a quantum material. And that's something that has a very funny definition. And the other thing that I'm going to tell you is that of all the people at this conference that I'm talking about that were here talking about quantum materials and high-temperature superconductors, we don't always agree on everything because it's so unsolved. So if you see tomatoes coming my way, you'll understand why. And then the other thing I want to get across is I'm going to talk about the gravity wave experiment, where they detected gravity waves through 20 years of building LIGO, which is the gravity wave detector. And I'm going to say that towards the end in this analogy. What we have in condensed matter physics or quantum materials is we're not looking for one thing like gravity waves. We're looking for many, many kinds of quantum materials. And we have a suite of new growth techniques, new measurement techniques, and new ways we can do theory and computation. And these are changing dramatically over the past 5 years. I'm always astounded in what I've learned this week. And I hope you get that analogy. The National MagLab has its main campus in Tallahassee. It's a large organization, has over 400 employees, and that's an overview. And what we have is the largest and the strongest magnet in the world. This is, I forget how many times it is, times a magnet that you stick on the refrigerator, but there's nothing like this in the world. And every time you tweak up the magnetic field on a new quantum material, you find something new. And it's a very exciting place to work. We also do some interesting things in MRI. And I'll mention, as I go through the talk, I'll show an example. And we also do, and I'll mention some other things, but I want to say also that we also have 2 user facilities at the University of Florida. One of them is a new kind of magnetic resonance imaging, and I'll give you an example. And we have something called high B over T. We get down to very, very, very cold temperatures, microkelvin temperatures at high fields. And there's a lot of things to be learned there. And finally, there's this pulse field laboratory in Los Alamos. And we can go to 101 Tesla pulse field. And I'll show you just a quick flash of some of the data that we've learned by doing work at the National Magnet Lab. So this is what my director calls our Delta map. And you can see that's Los Alamos, and that's Tallahassee and Gainesville. These are obviously the Delta hubs. That's why there's so many flights going in there. But the main idea is we have a lot of people that come and go. We publish a lot of papers, a lot of exciting science. And every year, 25% of our users are first-time users. So if anybody wants to go and do some experiments, go on the website, sign up. It's free to use it. You just need to get there and have a place to stay. I have a big house. But come and take a look. The other thing, if you just Google MagLab, it's really a fabulous website. There's all kinds of things for kids. And on February, I think 25th, it's the last Saturday in February, come to our open house. We have over 8,000 people that come every year. The major themes are materials, energy, and life. As I go through the course of this talk, I will mention this and this, but I just want to tell you that one of the things we do in energy is petroleum. And we can do forensics on oil spills, and we can tell exactly where oil comes from and how to clean it better. And also we're applying these now, besides petroleomics, we're doing some things on proteinomics. And so I won't go into that now, but you can see it all on the web. Enough of that. I'm going to talk about what are the defining properties of a superconductor. I assume some of you have been to some of these meetings, these lectures before and have seen this. I actually gave a Pagels lecture many years ago and talked about this. But the bottom line is a superconductor is not a perfect conductor. It does conduct electricity without any loss at all. So if you have a normal metal, like if this was made of copper or something, and you measure the resistance, as you lower the temperature, the resistance gets lower and lower and lower, okay? But in a superconductor, what happens is below a certain temperature, which we call TC, which means critical temperature, below that critical temperature, the resistance goes to 0. That's really hard to understand. No loss of power at all. But there's something else that goes on here, and it's called the Meissner effect. This was invented by Meissner-Ochsenfeld. Ochsenfeld was the graduate student. And when I give these lectures, I tell the graduate students, get your degree so you can start getting credit. But what happens is that it's hard to explain, and there's going to be some analogies in here. But it turns out that if you have a superconductor in a magnetic field, it spits out the magnetic field lines. Okay? It just spits them out. It hates magnets. And that was really weird. And it took a long time to figure out why. And there was an indication there was something going on that was quantum mechanical. Okay? So I have a warning here. There's going to be 2 fun slides of a lesson in quantum mechanics. Okay? And Feynman once made the statement, One never understands quantum mechanics. One just gets used to it. So if you feel like you don't understand it, that's correct. Neither do I. But you do get used to it, and we use it in our everyday lives. And what I'm going to tell you now are things that are predicted, measured, and used. But before I do that, I want to tell you how cold is actually cold. So here's a very famous plot that has a list. The y-axis up here is the temperature at which a material superconducts. So below that temperature, the material superconducts. And on this axis here is the year of discovery. And I'll mention that it was discovered in 1911. And the theory of the conventional superconductors didn't come out until 1957. So it's a hard problem. And there's many, many, many families of superconductors. These are the high temperature superconductors here. And they go up to what we call about 165 degrees Kelvin. Most of them superconduct about 100 degrees Kelvin. Now, how cold is that? Here's a list of temperature scales. So high temperature superconductors go up to about minus 163 degrees Fahrenheit. They used to be just much, much lower, like almost to absolute zero. Very, very hard to cool things down. Now, in low temperature physics, we use this Kelvin scale instead of the Fahrenheit scale. Because Fahrenheit isn't this is my thermodynamics lesson. Fahrenheit isn't a thermodynamic temperature scale. How do you know? If you go outside and it's 0 degrees out there, okay, that's pretty cold, 0 degrees Fahrenheit. And then you hear in the weather report it's going to be twice as cold the next day. Alrighty then. So the Kelvin scale, we use it because absolute zero is absolute zero. And if you go out into the middle of space, as far away as you can get, it's not quite absolute zero because of the Big Bang. There's 3 degrees out there. But we have methods of making things really cold. And that's a kind of a fun thing to do. By the way, the coldest temperature on Earth is minus 128 degrees Fahrenheit, 184 Kelvin. And you can see that's still above the temperature of the highest temperature superconductor. And so they're still really, really cold. So one thing I like to do in these lectures, especially the public lectures, is do a lot of demonstrations. But I have a clipped wing, and I'm not supposed to use this arm. So I just got some pictures from the web. So one of the things that I love to do is you take a bowl of liquid nitrogen. What is liquid nitrogen? Oh, let me go back. I didn't define that yet. So liquid air is about 77 degrees Kelvin. Okay? That's easy to make. It's cheap and easy to make. The old superconductors, the conventional superconductors, are much colder than that. And you have to use things like liquid helium. That's very, very expensive to make, and it's getting more and more expensive. Liquid air, or liquid nitrogen, is very, very cheap. And it's like cheaper than milk or beer, whichever you have your preference. So if you make this stuff, it's easy. You can throw it around. You can spill it on the floor and everything. And what I love to do is shrink balloons, because as things get cold, they contract. And so there's an example of pouring liquid nitrogen on a balloon and shrinking it. Another thing we like to do is take things that are soft at room temperature, and you freeze them, and you can crack them. The other thing I'd like to do, and I've done this many times, is if you're very quick about it, you can stick your hand in liquid nitrogen, you can pour it over your hand. Why? Because it's so cold. This is really, really cold. And what is this picture here? That's a frying pan. Has anybody made pancakes? Okay. So in the pancakes, you don't put the batter on the pancake pan until you spit a little water on it and they run around, right? That's because the pan is so much hotter than the water. And what does the water do? Underneath it like boils up, and it goes around and runs around all over the pan, like an air hockey table. And that's exactly what happens with liquid nitrogen on the floor or your hand. It makes this layer of steam, only it's liquid nitrogen steam, and it runs all around. So even though they're called high temperature superconductors, you got to get down to this temperature to make them superconduct. And one of the things we're hoping to do when I show you some applications is make the temperatures higher and also the materials more practical for some applications. So here's the warning of the quantum mechanics, okay? I apologize. It's just to get the feel of it. And then it helps with the analogy. So what happens? What is long-range quantum mechanical order? So if this clicker were a conventional metal like copper or aluminum, the electrons would bounce around in them, and you have, like 10 to the 26 electrons or something, a lot of electrons in there, and they're all separated. They're not just particles, though. Electrons are also waves, okay? And if this is made out of niobium or a high-temperature superconductor or some other thing, or whatever is in your MRI machine, and you lower the temperature, all these electrons hang out together. They fall into something called a single quantum state. So they go from not liking each other at all and not talking to each other to being really party animals. How does that happen? Well, that was the big question. Okay, and here it is. There's something that an electron has intrinsically, which is a little bit of magnetism. That little bit of magnetism is called spin 1/2. Sorry, I didn't invent the word, okay? It's just a property. But Mr. Fermi and other people have shown that when things have this spin 1/2, they can't be party animals. They have to avoid each other. Furthermore, electrons are negatively charged. Okay. Oh, so I'm sorry, let me go back here. So they can't go together, but if you can pair them up, and you have two spin 1/2 particles, you can make atom this way and get spin 1, or this way and get spin 0. So can we pair these little electrons up and make them an integer spin? Why? Because if they're spin 1 or 0, they're allowed to fall into a single state. Those are called bosons, okay? So bosons, that's a good name for a party animal. And they can fall into that single quantum state. But we have a problem. Electrons are negatively charged. So they're going to repel each other. How can you do this? And that was the genius of the Bardeen, Cooper, and Schrieffer theory that actually the person I mentioned earlier, David Pines, had a big role in also. Caution, analogies ahead. All analogies, if you push them hard, break down, but they sure help us think about physics. The Cooper pairing mechanism, they're called Cooper pairs because they're not stuck together in real space. They're not hanging onto each other. What happens, they're paired in something called momentum space, which means it's the motion of the electrons that are paired. It's okay if you don't understand this. Here's the analogy. The analogy is at high temperatures, everything is jiggling around like water boiling. And as you lower the temperatures, things cool down and move more slowly. And then as you cool the water down, it becomes ice, okay? That's the same thing true in a metal, okay? So metals, things are moving at high temperature, you cool it down. And then some metals and some materials have something that's called a strong electron lattice interaction. In other words, the electron really feels the lattice and the lattice really feels the electron. And so below a certain temperature, when it's not bouncing around like this attraction between the moving electron and the background is actually stronger than the thermal energy. And what can happen is that as the electron zooms through, it can bring in, because it pulls on the atoms, and it brings those positively charged atoms in, and it leaves a wake, and another electron sees that. Okay? So the analogy, and I like to stress this here because this analogy I heard recently in someone talking about gravity waves and LIGO, and I couldn't believe they took an analogy from superconductivity. It's called the soft mattress analogy. Okay? So you think about that, use two people on a really soft, squishy mattress, and they're going to roll into each other. But we don't have that in a superconductor because electrons repel each other because they're negatively charged. So we have two people in that bed that just don't like each other. Okay? Like, I really hate you, and we're stuck on this bed. So one of the people will grab the side of the bed, okay, and someone's in the middle, and they get out, and the person says, whew, relaxes, but there's still a depression there. And they roll into what the depression is left. So that's the best analogy I can tell you for Cooper pairing. So they're not paired in space. They're paired in this moving around kind of thing. And that gives you an idea that there's a distance, that the size of the mattress, how deep the mattress is. You can make good analogies for how strong this Cooper pairing is. Now, this perfect diamagnetism is the second property. And what happens, and you don't really have to know why, but as I mentioned before, the superconductors really, really dislike magnetism. And because of that, they turn into anti-magnets, okay? And they just say, if you put something in a magnetic field, it says, I'm going to make my electrons move in such a way that I'm going to spit out the magnetic field. And here's an example of magnetic levitation, if I could make this work. There we go. And this is amazing. See how look how stable that is. So there's a high temperature superconductor sitting in liquid air below, and that's a very strong magnet on top. And it really sticks in there. And in the next slide, I'm going to tell you why this works so well and why there's a great application to levitated trains. Here's an example of a superconducting, actually this is an example of a high temperature superconducting MagLab train in Japan. It's a prototype. This technology has existed for years. The Japanese had a levitated train that used conventional superconductors that went for less than a kilometer. But my Japanese colleagues were so proud of the fact it just went far enough to take their funding agents for a ride. So this is the idea of a type 2 superconductor. I'll show you when it was invented a little later on, but all practical superconductors are called type 2. And what that means is they allow a little bit of flux penetration. So these are magnetic field lines going through the type 2 superconductor. And there's vortices made out of these superconducting Cooper pairs. Okay? But the center of the vortex has the magnetic field going through, so it's not superconducting. So in applications, one of the things they worry about all the time is how do we pin those vortices? Because if these vortices can move, well, the center of the vortex isn't superconducting. It's normal. And so that's going to dissipate energy. So that's a big research area right now. And then this is something now that you can understand Colbert.
Ladies and gentlemen, are you ready? Then please welcome from the physics department at Ithaca College, Dr. Matthew C. Sullivan and the quantum levitator. Doctor, thank you so much for joining me. Now this is a quantum levitation track, correct?
It is indeed.
All right. Well, thank you so much for coming on to help me crush Jimmy with quantum levitation. Nation, as I'm sure you know, quantum levitation refers to the phenomenon whereby the magnetic flux lines flowing through a type 2 superconductor are pinned in place despite the electromagnetic forces acting upon them. I learned that from the inside of a Snapple cap. Now, Dr. Sullivan, can you confirm that if my ice cream quantum levitates, it is undeniably the ice cream of the future?
Absolutely. That's just science.
Okay, excellent. All right, here we have some of my Americone Dream. It's available in mini cups, which Jimmy's is not, okay? And I will confirm, that it is delicious. And now, are you ready to send my ice cream into the future?
Certainly.
All right.
The switch happened.
Okay. Ice cream of the future. Engage. It's
So the track of the magnet and the high temperature superconductor is in the cup.
Here, put it down for a second. There you go. Oh, Jimmy, look. Look, Jimmy. It's levitating. Eat it, Fallon. Eat the future. We'll be right back. Hit it.
Okay. So that to me is an important application. One of the first applications of high temperature superconductors was education. And so if it gets your excitement, that's great. And there's all kinds of great quantum levitation on the web if you want to look at that. But why do we need better superconductors? Okay, there are some amazing applications, things that silicon can't do. And that's what I'm going to mention here. I'll mention a few of them here. But the other thing I want to point out is the fundamental research. I don't have time to go into a lot of the details, but man, these things for decades, they just can't leave the field. It's so exciting, and it's how do these electrons, the quantum matter actually, are these electrons talking to each other over long distances? And how do they do that? How do they get correlated like that? And almost all high temperature superconductors, maybe all, that's up for debate, have these funny quantum matter states. So I want to show you some examples here, and this is a MagLab example. So we've probably, and I certainly had MRI recently. If you've been in an MRI, right, you get to go, yeah, probably if you're over 18 or something, you've been in more than one, you get to go inside of a superconducting magnet. Because to make really high fields that are kind of practical and not really complicated and easy to run, you need a superconductor. I'm going to tell you what kind of superconductor we use pretty soon. But what we do at the Magnet Lab is use very, very, very high fields to do MRI, or yeah, MRI, the imaging. Why would you do that? So here's something done at 21 Tesla. When you go into a hospital, your MRI is usually at 3 or 4 Tesla. If you actually were imaging the water, the hydrogen in your system, and wanted to look at 21 Tesla, you'd have to, what it is in MRIs, they put you in a field, and then they put microwaves on you, okay? If you're actually going to image water or hydrogen at 21 Tesla, you have to use such high frequency that it's like going into a microwave oven and it's like not real healthy. You get higher resolution, so you can do it on dead things, but not living things. But let's unlock the periodic table. Let's image sodium. Why sodium? Well, here's an example that I think is very intriguing. So you can buy a rat with a brain tumor. Very interesting. And we're imaging the sodium here. It's not high resolution, but you can see the sodium. And it's not damaging. The RF frequency, the radio frequency you put on the animal doesn't hurt the animal at all. And then you give the rat chemotherapy. You wait a few days, and you image again. Why is this important? It turns out that when cells are dying, they start uptaking sodium. And what was my surprise is we don't really understand why. That's okay. Most cancer research is statistical anyhow. We don't have to know why, but that happens. So if in 4 days nothing happens or you try another regimen, if that tumor lights up with sodium, that means it's been uptaking sodium. And that means the cells are dying. And that gives you some confidence that therapy might be successful. So that's pretty exciting. Other examples of superconductors besides MRI are in the energy regime. And I've worked a lot with the Department of Energy. And the basic idea here is that the grid is strained for capacity. And we want to use more and more renewables. And that's going to put more and more stress on the grid because we're going to have renewables from many different sites, sending on the grid here, there, and everywhere. And that's going to stress the grid more and more. And in the meantime, we lose about $79 billion a year in resistive losses in the grid. If we can find key places to put in superconductors in the grid, we'd have less resistive loss, power loss. Here's an example of one that was going to go forward, and the Department of Energy stopped funding it. But this is sort of cool. It's called the 3 Amigas project. It turns out that our grid in the United States is AC, alternating current. You got your 60 hertz, sorry, that you plug in. And it turns out there's 3 separate grids. There's the Eastern Interconnect, the Western Interconnect, and the Texas Interconnect. Okay, but the idea was they're separated, and if you have AC oscillating circuits, you can't just connect them because you're going to lose a whole lot of energy. The plan was to convert down to DC, and through underground cables with high-temperature superconductors, invert back up again. And then you could have seamless transmission of electricity across the entire United States. So there's all kinds of even Homeland Security reasons why you do want to do this, and I hope this comes back online in the research. Another example, there's also some of these out in the field now, is turbines. Turbines, as you know, are getting bigger and bigger, and they're getting to be the size of 737s. If you make the generator in the inside, instead of using conventional metals, superconductors, you can come up with a design that's less than half the weight of a conventional generator. And so that's going to be some real applications. And as I mentioned, you have to cool it. And just like the Tres Amigas project, you're not cooling a whole power grid. You're cooling a small area or a small generator. This is one that I like. This one's a little further away. There has been some in-ground testing. This is called SMES, which is superconducting magnetic energy storage. And all it is, again, it's an old technology. You just put a bunch of current in a toroid, okay? And let's say we're taking an energy you put it into this torus from photovoltaics. Okay, these are using solar energy. So there's going to be a lot more energy you're going to get when the sun is up, and a lot less energy you're going to get when the sun is down. Furthermore, these energy collectors, the solar energy collectors, tend to be kind of noisy. So you need a method to collect them, store them, and then bleed them out when you need the power and more smoothly. And these devices will do that. It's a little further down the line. What's so interesting about superconductivity is that it's a serendipitous discovery field. Okay? Kamerlingh Onnes, in 1909, there was this race for the coal, and he learned how to make liquid helium. It's made just like your refrigerator works, but you use high-pressure helium, and it goes to very cold temperatures, 4 degrees Kelvin, where room temperature is about 300, so it's really cold. And then once he did that, he and his colleague Holst decided to, let's see what happens if we cool down a metal. And they did that. They chose mercury, because mercury is a liquid at room temperature, and they thought it should be clean. And as resistance versus temperature, as you lowered the temperature, these were some of the predictions. And this is what happened. These are the data right from the paper that was published. The resistance goes down, and just around 4 degrees, the resistance drops precipitously to 0. And they studied this, and they learned all kinds of things. They made magnets out of it. In fact, Kamerlingh Onnes even made SMES things. He's a brilliant guy. They did amazing things. And there's a press release from the Chicago Tribune in 1913 where Kamerlingh Onnes is quoted as saying, this could have a profound impact on our energy crisis. So he was a man ahead of his time. Then the rest of the superconductors, when I showed you that superconducting transition temperature versus time, were found serendipitously. There was a gentleman named Bert Matthias who was at Bell Laboratories who just started mixing things in periodic tables. And in 1952, he mixed a material. If you look at, you can't see, but I have periodic table leggings on. I have a periodic table dress, but I couldn't get it on with my cast, so nerd, you know. Anyhow, I can tell you where you can find these on the web. So anyhow, Bert Matthias just used something that is a magnetic material, cobalt. It's a magnet at room temperature. And he mixed it up with silicon, which is a semiconductor, and he made a superconductor. So who understands that, okay? And he had these certain rules, and this was one of my favorite ones. Stay away from oxygen, magnetism, insulating phases, and theorists. And if you want, he was a very interesting guy. And I will just tell you that this was all correct for conventional superconductors, but for the high temperature superconductors, we need oxygen, magnetism, insulating phases, and I think we need theorists. So there's some nice things if you want to read, and there's Warren Pickett is here tonight, and he wrote an article, The Other High Temperature Superconductors, when I go over how unsolved these are, that what if the first superconductor that Kamerlingh Onnes discovered was one of these unconventional superconductors? It's actually pretty funny. But I want to stress, having a room temperature superconductor is not going to be enough. Like I mentioned before, you need a type 2 superconductor to carry current, and there's other constraints. If you make a really good high temperature superconductor, but you can't use it, it's no good. So what happened was John Hume discovered a kind of material that really is like the original high temperature superconductors, okay? They, as far as just the temperature goes, they were much higher temperature. You still needed liquid helium, but they conducted at much higher temperatures, and they were actually strong, so even high magnetic fields, they would still superconduct, okay? But they're hard to use. So later on, he found another material, and this is the workhorse of the field. This is what's in your MRI machines. It's something called a random alloy called niobium titanium. This material, niobium titanium, actually does not have as high a TC, okay? Can't take the fields as the other materials, but since it's malleable and reliable, it's a better superconductor. So remember, a better superconductor isn't just a higher temperature. It can take the fields, and you can put it in place. So this is what's used in the supercolliders and wires and what's used in your MRI machine. And I remember my boss at Bell Labs made the statement, high TC gets Nobel Prizes, being able to work, be practical, saves lives, hence the MRI. So we have something that really changed the way we look at superconductors. And this was the discovery of the first unconventional or high-temperature superconductor. Frank Stegler, who's here in the audience tonight, discovered a material that has huge electron masses. So you could measure the electron mass using measuring heat properties of materials at low temperatures. And you get these masses being 100 to 1,000 times the free electron mass. And that has to do with the electrons correlating with each other. It's not just the way the electrons feel the lattice. It's how the electrons talk to each other. Then, not too long after that, Gil Andrus discovered this. He took one of these heavy electron materials, and he put pressure on it. And this was the first of the domed phase diagrams. So what this picture is that this axis here is temperature, and this is pressure, okay? And as you apply pressure, the superconductivity occurs. And a whole lot of these materials were studied. But what's really interesting, if you look at this phase diagram, at low pressure, this material is at AF, means it's an antiferromagnet, but just leave it alone, that this is magnetic. It's magnetic. So at this side of the phase diagram, the material is magnetic. And at this side of the phase diagram, it turns out it's like a normal conventional metal. And in between, where they meet, superconductivity appears. That was weird, okay? All of a sudden, as they're discovering these materials, not only are there strange electron correlations going on there, but magnetism seems to be good for the superconductivity. So that was a very important discovery. And then what happened is there's many of these serendipitous discoveries or predicted discoveries that led us to the high-temperature superconductors. And I like to put this up here just to say one thing. It doesn't matter what these materials are or what they did. These are amazing scientists who are brilliant and work all the time. Okay? They work like dogs. And they really each have one hit. So if we really could predictively design new superconductors, you would have more than one hit. You would find a way to discover new families of superconductors. And so what we're doing right now here and in our center in many places is trying to understand how these materials work. So here's that picture I showed you before. Okay? So this is the temperature below which any of these materials superconduct. And this was the year of discovery. Here's Kamelich Onus discovering mercury in 1911. Okay, and here's some of the materials that I mentioned before. Okay, here's the high-temperature superconductors. Now, I want to stress a couple things here, and that is that, number one, most of the families of superconductors aren't even on these plots. There's about 50 of these families that we've been able to find that have a lot of different properties. Okay? And I also want to stress another thing. This line here in red, okay, these are what we call the conventional superconductors. This is one of the two problems of correlated electrons or quantum materials that's solved. And I'll go over that again. But we saw that mattress thing, the BCS, Cooper pairs. We understand how those work. We really understand them. Okay? And this BCS theory, when it came out, just worked. And it explained all the properties that we're seeing, and it predicted new things. Everything not in red here is what we call an unconventional superconductor. And they have a few things in common. And this whole conference this week is what's in common and what's not in common. Okay? Well, one thing that they pretty much have in common is what we call I should have changed the word to quantum matter there. But the electrons have these funny states. So here's another phase diagram with a dome in it, okay? Just like I showed you in the last few graphs. I'm sorry, that shows my age in the last slide. So this here is temperature again. And this across here could be pressure, or it could be mixing in new materials so you can change how many electrons or holes or whatever, how many carriers are in there. You can tune it with magnetic field, but it's some variable that you push on it. And almost every one of these materials has this phase diagram. And what do we have here? On the left side, it's typically magnetic, and a kind of funny kind of magnetic state typically. It could be an insulator, okay? Or it could just be a terrible metal. But it's an interesting magnet. And way over here on this side, it's typically, by the way, this isn't 100% true, but I'm using typically because there's a lot of variety of these materials. But on this side, you typically have a simple metal, okay? And in between, you have the superconductivity, okay? What's very interesting about this is that this is pretty much a solved problem, okay? And I'll go over this again, but if you take a look at a simple metal or a semiconductor, theorists can pretty much calculate what the electronic properties are, the optical properties, thermodynamic properties. And what they do is they look at the lattice, and they look at what's in the lattice. And there's ways they can calculate from the shape of the lattice, the structure of the lattice, and what the atoms are in the lattice, and calculate how well it's going to conduct, how well it accepts light, things like that, okay? That's also true under this dome here, okay? Under the dome, no matter how unconventional the superconductor is, they're all Cooper pairs. Now, granted, they have some interesting properties, okay? But after this BCS theory came out, there are some mean field equations, we call them, that you can now calculate these properties. We don't really understand exactly why these materials are superconducting. We don't understand exactly why the Cooper pairing occurs. It's not only the interaction with the lattice. It has to do with magnetism, and that word that I used before, spin. But you basically can describe the properties because they're Cooper pairs. The quantum matter is up here where this star is. That's where the strange properties are. So this is just to show you there's more than 50 families. And here's the one I showed you before. Here's some domes in an organic superconductor. These are the high temperature cuprates. These are something called dichalcogenides. I could put up a whole bunch of these things. But it's very interesting that they have a lot in common. But I also will say that this area where you have this funny star here, where you have the quantum material, quantum matter, it's really quite different from material to material. So I really kind of have the feeling that if we're going to attack and understand all these families of materials, this is my view, so the scientists in there, you can get angry. I think you better study these materials, distinct from these materials, distinct from these materials. Physicists love Occam's razor. There's going to be one theory of everything, okay? Well, my viewpoint is just like when I talked about cancer before, there's not one theory of cancer. If you have breast cancer, there's many, many kinds. Estrogen positive, estrogen negative, HER2, okay? And you target them separately. So my feeling is there's enough in common, but there's also enough distinct from these materials that they're going to take different theories. Oh, that's just to show you that even in higher energy physics, there's a phase diagram, what they call color superconductivity. It's amazing how we, coming from different places, we all tend to agree with each other. Okay. So what is this quantum matter that I'm telling you about? If you don't understand it, we're here together, okay? So that's what we're talking about all week here, okay? So in a simple metal, as I said before, we can understand by looking at the structure and what the atoms are, okay? We know how to do that pretty well with simple metals. And as I mentioned before, in a superconductor, we can describe Cooper pairing, so we can tell you what the electronic, optical, and some of those properties are. The general definition is that that doesn't work. Oh, I have a typo up there. That doesn't work. And experimentally, we find these very, very strange things happening. There's something we call nematicity, because a nematic liquid crystal looks like sausages, and the electrons group together in the sausage phase. Another thing is stripes, where the electrons kind of line up over long distances, or they get really heavy. So those are the kind of things we study. So it turns out that for conventional superconductors, this is solved, as I said before, and for both above and below TC. That's the background. You throw in electrons, and we can get the properties. We know that the electrons interacting with the lattice gives you superconductivity. These are solved. unconventional superconductors. At the far right side of the phase diagram, it's a simple metal. Under the dome, it's Cooper pairs. So this is not an honest thing because it's not necessarily electron phonon, but there's something causing the Cooper pairs there. Up here, which we call the quantum matter, it's got these funny shapes here. And here's like an artist's rendition of nematicity. So it could be like 10 lattice constants long and 1 lattice constant wide, these cigars of electron clumps. Like, how weird is that? And there's been a lot of just fabulous talks here on it, and boy, I've learned a lot. Oh, that's supposed to say unsolved. I have a typo. I was tweaking my talk up until last minute. So this should be solved, solved, and unsolved. I will. By the way, I used to study something called time reversal symmetry breaking, and I find that I often fix my talks after I give them. So bear with me. Intriguing point about this dome, okay? It's been pointed out by some really brilliant people that these things here, these funny quantum matter, okay, if it's too strongly correlated over here, well, a dome is high in the middle and low on the side. This is where the superconductivity occurs, okay? Over here, when it's weakly correlated, where there's no quantum matter, it's like a simple metal, TC is lower. And over here, where it's really, really strongly correlated, TC is lower. So there's some argument here that these strong correlations, if it's too strong, it's actually bad for superconductivity. Somewhere in the middle, it's good. So these kind of quantum matter strong electron correlations are bad for high temperature superconductivity, but you don't get high temperature superconductivity without it. So there's some interplay we have to understand between the Cooper pairing and this other quantum matter that will help us find what a high temperature superconductor is. And here's an example from the MagLab. So this is one of the people who did this, 2 of the people that did these experiments are here. What we have here is this is the dome. And as I mentioned before, if you put on stronger and stronger magnetic fields, you can kill the superconductivity. Well, these super high temperature superconductors, the ones, this is called the cuprate, have they can really take a lot of magnetic field. And they're the highest TC practical materials out there. So what we do is we measure the dome, okay? And as we put in higher and higher fields, okay, we start killing the superconductivity. What they're finding, what this measurement shows, is that, in fact, as you go down into this dome, the mass of the electron starts diverging. Ooh, that's weird. But the whole point we want to get here is that we have the magnetic side here and the simple metal here, and there's some fade transition. We want to get down there and see what's going on at that point. Maybe that will tell us what the origin of that high temperature superconductivity is. Just an example. So some examples of quantum matter, as I mentioned before, there's dozens of them. And so this is the example of the nematicity. Okay? This is an example of heavy electrons. This is some other kind of clumping. John Tronquata discovered the stripy behavior, and he's here too. I'm here with all these like really great physicists. It's so exciting. So this is going to lead to my analogy. So we have a couple more minutes here. This is Sushitra's example, and this is Sushitra. So what we have here there's all kinds of, I'm not even going to use these names. I do some of these measurements. Other people do some of these measurements. And these kind of measurements we see, these are called quantum oscillations. You put the material in a very, very high magnetic field, and the electrons go around like that, and you change the angle, and you could kind of map out what the electrons are doing in there, and how heavy they are, and how they're moving around. It's just amazing. These things weren't even possible a few years ago. And there's many, many other things that are done here that weren't even possible. But it's not just the measurement. Paul Canfield gave the lecture here a few years ago, and he talked about growth. And the experiments that I do some growth myself, but the experiments I do are only possible because of the amazing steps forward people have had in crystal growth. As these materials get cleaner and cleaner, you can understand more and more of the intrinsic properties. And the other one that I'll mention is that the techniques of computation have also we have Pierce Coleman and Kotlier here and some other people that have just changed the face of computational physics, and it's getting better and better. So now, warning, analogies ahead. So I was lucky enough to hear Kip Thorne give a lecture when he got the Kavli Prize. And maybe you've seen this before or you haven't, but this is a picture. I took a picture of it, and I went and I talked to him, and it took me 56 hours to make the analogy. But he won the Nobel Prize in Physics this year, and this was for the detection of gravity waves. And this is the standard picture, and I'll go over this again. What we have here is the sun and the earth, and this is a two-dimensional representation of the four-dimensional, some people think many more dimensions, space-time continuum. You've probably seen this before. You're here at a public lecture for science. You've probably heard of some of this. If not, I'll remind you. I saw this picture, and I go, oh my God, that looks like BCS. There's something distorting there. So I was telling all my friends about it after the lecture, and they decided I was completely crazy. So it took a little effort there. Gravity. Mr. Newton came up with his 1/r² law, and it explained a huge amount why the apple fell on his head, why the Earth is attracted to the sun, why we're attracted to the Earth, okay? Why, as you move further and further away from something, the attraction gets less, okay? Mr. Einstein said, doesn't work all the time. There's a few places it fails. One of them is looking at the orbit of Mercury around the sun, okay? Newtonian mechanics almost explained it all, but it didn't explain why that orbit doesn't stay in the same place. So it's an elliptical orbit, and that ellipse moves. And there are a couple other problems. And so Einstein, and how did he do that? Because he was Einstein, okay? He came up with an idea, which is the microscopic theory of gravitation, that gravitation is a distortion in the space-time continuum. The two-dimensional analog is a rubber sheet. You put a rock and a marble on it, and they're attracted to each other, okay? So this looked like it was a good idea, but he also predicted that if really, really massive things banged into each other, okay, like you bang two rocks together in a pool of water, you'd make all these waves, and those would be ripples in the space-time continuum, okay? And he said no one will ever be able to prove this. Now, I'm going to show you this analogy is that they did prove this very recently. And what they want to use this for is maybe explain the question of most of the mass in the universe, which is dark matter. Or you may have heard talks on dark energy. Yes, I have no idea what it is, but it's there. We can't understand it. Mr. Fermi and Mr. Landau showed us originally, pretty much, and then a lot of good work happened after that, about conventional metals. Bardeen, Cooper, and Schrieffer explained a place that didn't work, one of the many quantum materials. Will our suite of measurements techniques help us understand quantum matter? Just to remind you of this, okay? The gravity wave detector LIGO. This was 20 years in the making. It is totally amazing, okay? These are I forget how many kilometers long, to measure, and they're looking at a little bit of light. And what happened in 2016 was they detected the first gravity wave. And what it was a black hole that was 25 times the mass of our sun colliding with another black hole that was 35 times the mass of our sun. Kaboom. This was many times the energy luminosity, if you could measure it that way, of the universe. But it's hard to measure. Gravity waves are small. But they measured it. And this LIGO detector, and it's not just one detector, it's many detectors. There were huge amounts of checks and balances. It's an amazing experiment, okay? They measured this, and you know what it was? It was a motion that was significantly less than the width of a proton. okay? And they've had other measurements. Not only have they measured black holes colliding, they've measured neutron stars, amazing stuff. So what do we have here? Our quantum matter detectors are new areas of crystal growth, new areas of measurement, and new areas of computation, okay? So here's my analogy. This is my second last slide. I hope I'm doing okay. Oh, I'm a little late. So the progress. Newtonian classical gravity is forces between objects are derived from masses and position, okay? Simple metals, properties are derived from crystal atoms and their positions in the lattice. General theory, masses create a distortion in the background, which is the space-time continuum. In simple superconductivity, electrons create distortions in the background, which is the crystal lattice, okay? And, oh, this got cut off at the bottom, I apologize. And what Kip Thorne's message was, now for the first time with LIGO, we have a way of looking at the universe with something that isn't light. For the first time, gravity waves. Now, what we have in quantum matter is we have all these techniques. Will the suite of techniques help us understand our multifaceted questions that are so old and fundamental of quantum matter? So this is my conclusions. Hopefully, this will help us design better quantum materials, better superconductors. There's something that I didn't have time to put into, but one of the things that might make this is something called quantum computing. And superconductors are in the running for making quantum computers. That's a whole other talk. And will our new tools be our LIGO to understand quantum materials? And I thank you for your time, and I'll be happy to take questions.
Of course, you just heard after this wonderful talk, Laura is happy to take questions.
I'm going to ask about the quantum computers.
So when you look at all those different families, I can understand the lattice.
All those different what?
All the different families of
Yeah.
the superconductors. For the very simple ones, the lattice is very easy to imagine. For those ones that have, like, 6 things in the, how do you guys look at those as lattices? Because you sort of say, well, at this end it acts like a simple metal. To me, it doesn't seem like there's much simple about something that has that many different sized atoms in it.
Well, basically, if you go, it's very, we'll call it high doping. So you put in, like, a lot of oxygen in, or whatever. There's things you can do that. You just do the measurement, okay? You look at the optical properties, okay? You shine light on it, and you see what reflects or gets through. You measure the resistance as a function of temperature. You do what the heat transport is at low temperature, and it acts like a normal metal, even though you've got tons of elements in it. And even, a lot of the materials that we use practically don't just, our wires aren't just copper. There's many materials. So that is done just by the measurement. You make the material, and then you measure it, and it acts like it's supposed to act. So it's just, it's not predicted to act like that. It's just how the measurement comes out. Okay? No one's asking about the quantum computers. Yes.
So in high school and college, there's these nice tables that shows you the mass of an electron. So if you're gaining mass, and I assume I thought that's what you were saying.
I am, yeah.
The electron. Then is that as a clump of electrons are gaining mass, or a single electron is gaining mass? And does that have any implications for, or any theories about the subparticles?
Yeah. So we sometimes call this fractionalization or whatever, but what happens is these electrons interact with each other. So you can actually get the mass of simple metals just by doing the calculation, looking at the lattice, what's in there, and you get the mass, and it has to do with how they travel through the lattice, okay? What happens in like these heavy electron materials is that the electrons interact with each other, okay? And they feel each other, and they get these tugs. And so it's not picking up an electron and weighing it, okay? It's measuring the heat transport. And when you measure the heat transport at very, very low temperature, that gives you the mass. So what it tells you is these electrons are feeling each other so much more strongly than the lattice, and they're slowing each other down. That's distinct from the clumps. That's a different kind of quantum matter. And the clumps are like these, the nematicity clumps or the stripes, et cetera. So again, these are all quantum matter, but they have different flavors. So. Yeah.
So I understand you still have a lot of things to solve for the quantum matter. And do you think that by solving that, you're going to understand how a superconductor becomes a superconductor?
Yeah, that's like the Holy Grail, okay? Well, there's two Holy Grails. We really do understand how a conventional superconductor works. But all those rules that we have doesn't help us design new superconductors, okay? Now, in the high temperature superconductors, or these other many families of superconductors, we don't really understand why they're paired. But we have a lot of rules, like this is good, that's good, but we still can't design the superconductors. It's my personal belief, and this is only a belief because it needs to be proven, and we need to do the experiment. But by the way, that's quantum mechanics. You invent a theory, and then you go into the laboratory to prove yourself wrong or right. But it's my personal belief that if we study how this quantum matter occurs, how this clumping, this heaviness, these stripiness, and other things that happen, if we understand that, will that help us really understand why they superconduct, and will that help us design better superconductors? Maybe. Will LIGO give us dark matter? Okay, so that's what we are hoping for. And that's why they call it research. So
Back here.
Do you see anything akin to Moore's law for bringing your temperatures up?
oh, what a good question. Yeah, so Moore's law is like this incremental advance. And so there are certain areas in our field, like the quantum computing field, and certain, the quality and the computation has incrementally advanced. But as far as moving up the superconducting transition temperature, I don't know how that one thing that has advanced, like in a Moore's law, is finding better ways to pin those vortices. But as far as designing whole new families of superconductors, we're hoping we get to a Moore's law. But that would be a great idea. I love that analogy. Thank you.
Okay, if there are no more questions.
Oh, wait.
One more, here.
I guess maybe a couple things. Do you see any periodicity at all regarding electron matter in this situation?
Oh, yes. Yes.
Okay, so you do see periodicity.
Great question. How did you know?
Then my next thing is, so when I take a look at smaller, ultra low mass galaxies, there's a huge association with accelerated rates of movement of stars in those low mass galaxies, which is an indirect indication that there's dark matter there.
Mm-hmm.
And you, previously you were pointing out how there was association with stellar development with some of this in dark matter, dark energy, and so forth. Is it possible that there might be, for instance, even in formation of things like black holes, that there's a release of time and space being converted from mass and energy as it goes into the black hole, and then the gravitational waves are perhaps not just purely gravitational, but also perhaps partly time and space being released?
It's a little out of my realm. I know some people have tried to take this analogy a little more accurately. So there certainly is mass to energy conversion. Okay, that's what happens in nuclear, atomic bombs, nuclear bombs, and power stations. There's certainly mass to energy conversion in stars, right? That's what makes stars shine, is the protons fuse. So I would like to think about how to make that really interesting analogy and apply it to this. I just haven't thought about that. One thing, and you're just making me think about this, what a great question, is that in fact, when the Cooper pairing occurs, that does lower the energy of the system. That's why it happens. So there might be an interesting analogy there that I'll think about. Thank you.
Thank you.
Okay, if there are no more questions, let's just thank Laura for a wonderful lecture.